Now, we will see other step in our signal conditioning and processing unit. So, if we recall our block diagram, if you go back to and visualize our block diagram, we will see this ECC amplification sometime later by the end of the experiment, and we have done the filtering part, which is nothing but a pre-processing part, which are we require especially like low pass filtering, high pass filtering, as well as notch filtering. Now, next step is what? If we recall our previous session, we require, in order to find out our BPM, we require to know the QRS peaks. How many number of QRS peaks obtained within a minute gives the measurement of our BPM. So, in order to find out that BPM value, how do we determine this is our peak, QRS peak, and when we see that peaks can be either a positive peak or negative peaks. Generally negative peaks are called valleys, but when we design a circuit, no matter what, either it may give the positive peak or a negative peak, and since we are interested only in a positive peak values, if we can pass through an half wave rectifier, the negative peaks will be completely removed off. So, that is the reason we are interested in, or we have to design a half wave rectifier, but it is not mandatory to have a half wave rectifier. Even simply we can go with a positive peak detector and a thresholding circuit, and we can implement that too without having a half wave rectifier too. But if you have a half wave rectifier, we do not even have to worry about the negative peaks at all. So, now how do we do an half wave rectification? Half wave rectification using an op amps. If you remember, op amp generally in case of any rectification, the first and the important passive element, the important active element that we take is nothing but our diodes. Diode plays a major role. Diode plays a active role even in case of our filtering from AC to DC. So, one step is our rectification, where half wave by using a diodes we will convert our AC signal into pulsating DC, right. So, the problem with simple element is impedance matching. So, that is the reason if you want to have some gain as well as some kind of an impedance matching, rather than having a simple diodes, if you can go with an diodes with an operational amplifier, it will always have a better advantage. Now, if we see our half wave rectifier, so since we require to remove our negative signal, right, as our intention is to find out our positive peak, the negative peak will be rectified using this half wave rectifier. Now, how does it work? If you clearly see that, right, the input is connected to the positive terminal, and forget about the diode right now. How does it, if this diode is not there, how does it look like? It is nothing but our half wave rectifier, sorry, it is nothing but our voltage follower. Now, how does an voltage follower works? What are the input that you give, output will also be the same. So, and the gain of the voltage follower is 1. So, whatever the input amplitude, the output will also have same amplitude without not having any change in the shift, phase shift. The reason is the input is applied at the positive terminal, but now in this case if you clearly observe, there is a diode, only one particular amplitudes will be allowed, and the amplitudes below and the negative amplitudes cannot be allowed, right. So, when the diode is in a forward bias condition, it will allow the input signal. When the diode is in reverse bias condition, it will not allow it, right. So, to understand about the circuit, what we do is that we can understand, for example, like say if the input is a positive peak, what supposed to be the output? It should also be positive peak, right. Now, because of this positive peak, the diode will be in a forward bias condition, so that we will get a positive peak. Now, during a negative peak, since it is voltage follower, right, we will get a negative, and diode will be in a reverse bias condition. So, we will not get anything, right, but diode will have some cutoff. Okay. Ideally speaking, we will not get any negative, and similarly another positive peak like that. So, as a result, when we pass through this circuit, we will get only a positive peaks, right. Why do we have to go with this circuit? Because when we see our ECC signal will also looks like something like this. Oh, since our interest is only this QRS peak, right, and we do not have to consider the negative, and this is nothing but a unwanted signal. So, what we can do is that we can remove this particular the signals which are lower than this value, right. So, that means the negative values can be completely eliminated, removed by using this R half wave rectifier. So, to understand that we will do simulation. Now, what we require? We require a diode. Let me take op amp as well as diode. Let me take op amp as well as diode. Then we require a resistor. So, negative terminal should be connected here, and this is RL. Any resistance value is more than enough at this point. Even we can go with a 10 K, it will not load the input. So, let me take it as 10 K resistor. Now, to understand the working of the diode, working of our half wave rectifier, what we do is that we will connect a sinusoidal input free signal, working of the circuit, connect a sinusoidal input signal, right, and the peak to peak value is 2 volts, because this signal is generally used to represent a peak voltage itself. Since we require the positive peak and negative peak as an input signal, so that easily to understand whether it is passing only the positive peaks or positive as well as negative peaks. So, we can take peak to peak as 2 volts. Then to visualize both input and output, I am connecting green represents our input signal, and other one blue represents our output voltage. Now, when we go to the grapher and run the circuit, right, if we observe the green is nothing but our input and blue is nothing but our output, when we see that the green is completely right full wave with a peak to peak of 2 volts, right, peak to peak value is 2 volts, but whereas on output if you observe, it was only allowing a positive peaks to flow, whereas the negative peaks is completely removed off. So, even if you consider an ECC signal in the same way, only the positive portion of the ECC signal will be allowed and the negative portion of the ECC signal will be removed. So, that now it is easy to understand the positive peak from the data, from the signal, and we can set a threshold. Now, here comes our thinking. Why? The reason is, when we recall what we had discussed about our ECC signal, till this part is okay, but how do we find out this particular voltage is a peak, and how do we set a threshold to the system, right. So, as we know that if we keep a capacitor will charge to what value, to whatever the output we receive. So, from that we can understand that if I use a capacitor, if the voltage is increasing, capacitor starts slowly, right. So, it will, since if we do not create any discharging path, whichever the voltage that we get, highest voltage that we get, capacitor will be charged to that highest voltage value, that is good enough. So, it is easy to understand the highest peak in a AC signal. What I mean is that, suppose if I pass the signal to a capacitor, so if the complete signal is passing through this, since the maximum voltage is at this particular value, right, and if I do not create any discharging path, the capacitor will always at this particular point. But how do we set a threshold, right? The idea is that if I can set a threshold, if we recall what we have discussed in our first session of our experiment, if you recall, if I can set a threshold and if I can find the peaks, how many number of peaks above this particular threshold points, that completely gives our the number of peaks in particular duration of time. But why do we have to consider? The reason is, when we see the peak, this also will be considered as a peak, this also considered as a peak, right. So, if I do not consider the threshold, even these things can also be considered as a peak, and it is very hard to understand the BPM correctly and accurately. So, that is the reason, as we already know that the QRS peaks is very long, are having a very high amplitude compared to other peaks. If we can detect this particular peak, our problem is solved. So, in order to detect that, we are using capacitor which stores the the complete highest voltage, but how do we create a threshold, right? And if I can create a threshold, if I compare the output signal from the input signal, so when you do the comparison, whichever is the highest, that I can decide it, right. So, if you see the logic to implement it, so this particular capacitor part will charge, and the purpose of this 1 mega and 2 mega is to provide threshold. But what percentage of threshold we are doing here? So, if you observe, suppose if I say this is nothing but voltage divider circuit 1 mega, 2 mega, if I say this is V in, so this is what V out. V in is the charge across our capacitor, right. The capacitor will be charged to the R voltage value. Let us consider that V in. So, V out is nothing but V in into 2 mega divided by 3 mega. So, 2 by 3 is how much? 66%, right. 2 by 3 is 66% of V in. So, that means we are setting a threshold at 66%. If you want to set at 75% or if you want to set at 50%, even we can change the resistance value such a way that it will always gives 70% or 65%, whatever the percentage that thresholding that we required for. Now, why do we are choosing 1 mega and 2 mega resistance? Why not 1 kilo, 2 kilo, 100 ohms, 200 ohms? The reason is that the input signal should not create any loading of our input signal. When we choose a lower resistance value, this resistance requires some current to operate, right. So, because of that we cannot, it creates a loading on our input signal. So, in order to not to have any effect on our input signal, what we do is that if I can take a very high input resistance, it will not load the input signal. So, rather than going with 1 kilo or 100 ohms, if I go with a mega ohms, the the loading effect will be good. So, that is why we are using 1 mega and 2 mega. So, then whatever we get is nothing but the signal which is greater than this threshold. This threshold is 66.6%. So, you will get a signal like this, right. We will see what we do is that in a simulation we will pass sinusoidal signal and we will look at this point without this particular, we will see whether the capacitor is charging to the peak value or not. Now, we will take even this particular portion, this portion 2 attached to that, and we will see whether it is setting a threshold and it is passing only the values greater than that particular threshold or not, right. And we will also compare with experimental results. Now, we will see how to implement the circuit using a simulation. Once we verify in a simulation, we will see in actual way and we will do the experiment on that. So, just open Multisim. If you recall the circuit what we have discussed, just recall the circuit. So, we need this particular part. So, I will take an op amp, right, and I need to have a diode. So, I will take a diode. Then we will take resistors as well as a capacitor. I am taking resistor, one more resistor and a capacitor too. So, capacitor is also there, then this resistor, right. So, these two has to be connected together. Now, if you remember, the purpose of a capacitor is to charge to a peak value. So, whichever the value that we are that EC signal peak value is there, that will be charged inside the capacitor. Now, the purpose of these resistors are to provide a threshold. Now, we are setting a threshold using 1 mega ohm resistor and 2 mega ohm resistor. So, when we calculate, if we recall, it is somewhere around 66%, right. So, I am taking 1 mega as R1 resistor and 2 mega as R2 resistor. Now, we have to connect this terminal to this one, right. So, this is the input signal. So, in order to test the circuit, what we use? we generally go with AC voltage. So, let me connect the AC voltage here, connecting here, and we also need a ground. So, I am taking ground, connecting here from here to here, and even this part should be ground. So, what we have to do in using this circuit, what we have to measure? We will see what is the output voltage at this, whether when I change the voltage of the input, whether the capacitor output. So, in order to understand, what I do is that let me remove this part, this particular terminal, so that there is no connections here. So, we can easily see whether it is following the peak or not. Then we will make this connection, and at this particular terminal, at this particular junction or at this particular node, right, we connect another voltage output, nothing but our we will connect it to a probe, and we will see how the output signal looks like, right. So, whether it is giving the threshold of our requirement or not. Now, I will take two probes, one at the input, so which measures the input voltage or whatever the input that we are connecting to the op amp, positive terminal, and other one at this particular point, right. So, the green it represents our input and the blue represents our output of the op amp. Now, to understand the circuit, let me go to the grapher and run it. See what we can see, the green is completely input, right, the blue is output, output is always showing it as 1, right. Let me stop it. So, if it is showing the 1, how do we understand it? Now, if I zoom completely, zoom all, and let me zoom only to this particular portion somewhere around 159 milliseconds, right, and even to 10 milliseconds I will zoom, right. If we observe, the output initially it is keep on increasing, meaning it is charging, the capacitor starts charging, and it is charged to a value of 1. Why only to 1? Because the input voltage, the peak voltage that we applied is only 1 volt, and since we do not have any discharging path, since it is a maximum voltage that the output is providing, it is the capacitor is always at this particular point. What if I change my output, right? What if I change my input? If my input voltage changed, if the input voltage is 2 volts, slowly again the capacitor starts charging to the 2 volts value. Why do not we see that? So, the whole idea of this circuit is to find out the peak value, and the purpose, whether it is the purpose is solving or not, let me check. So, let me run continuously, and I am running it continuously. Now, this voltage I will change it to 2, 1.05 to slowly to 2 value, 2 volts. Now, it is at 2 volts. Now, let me change the settings of the grapher to voltage. If you observe now, the capacitor started increasing to a value of input peak value, right, is not it? Now, what if I decrease? Let me decrease, right. Now, the capacitor started slowly decreasing, because the input voltage now is very smaller, and the capacitor will also take some time to discharge. So, because that entirely depends upon the discharging rate. So, that is why it started discharging, and again continuously maintaining the value of the peak. So, that means one part it is clear that whatever the peak voltage that we are getting, the capacitor will charge to that peak value, right. Now, what is our other purpose? We have to see whether it is providing the threshold of our requirement or not. So, in order to understand whether it is providing or not, what we do? We will connect this R1 resistor and we will take another output voltage, connect at this point. Now, this particular terminal I am not interested in, I do not have to. So, what I will do is that let me run, and yeah, even if it is there, no problem for us, right. So, this indicates our the output voltage at this particular point, and the violet color indicates the threshold. That means the output voltage at the threshold at the junction or node point of both the resistors 1 mega and 2 mega. Now, based upon our calculation, based upon our calculation, what is the threshold value? So, if we recall the potential divider circuit, it is nothing but V in into R2 by R1 plus R2. So, in this case V in is, for example, like say V in is 1 volt and R1 is R2 is 2 mega, R1 is 1 mega, 2 by 3 is 66.6, right. So, that means if the input voltage is 1 volt, the output, the threshold point is somewhere around 0.66 millivolt. 660 or 0.66 volts, right. Now, so to understand that, let me change the input voltage to 1 volt. Now, observe, right, 664 millivolt. That means it is properly following the required or whatever the threshold point that we set, right. If the input voltage is changing, even the threshold value will change, and how fast it changes, everything depends upon the capacitor value that we choose, that we have chosen there. So, in this case we have chosen 1 microfarad capacitor, right. So, another requirement in order to do the signal conditioning circuit or signal processing circuit of our ECG is completely fulfilled using this circuit, right. Now, what is the other part? What is the other part? Now, once we detect, once we understand which are all voltages or which are all the input signal is greater than this particular threshold, only those output signals has to be passed, right. Now, we have said this. Now, what we have to do? The input signal should be compared with this particular threshold value, and whenever the input value is greater than the threshold value, only that particular value has to be pumped out. So, in order to do that, what we have to use? We have to go with a comparator. Simple comparator is enough. We do not have to go with any Schmitt triggers or anything. The reason is, we are not setting any two thresholds here, we are using only single threshold. If the input value is greater than this particular value, only that particular signal has to be passed, and that has to be detected, and that has to be counted. So, depends upon how many number of such a pulses are we are getting, and if you use a counter there, then we can automatically see the number of pulses we are getting per second or per minute, anything. Now, in order to do that, we will implement other part of our circuit. When we look into our presentation, right, this particular part we have seen, and if the input signal is sine wave, if the input signal is sine wave, right, then at this particular point the output will be completely, because of the capacitor, the output is charged to the particular value, that is nothing but the peak value. So, that means we could able to see the peak value. Now, this particular point we can also create a threshold. Now, next part is identifying and generating a triggering pulses if the input voltage is greater than the particular threshold value. So, in order to do that, what we will be using? We will be using a comparator. We will compare the input signal, with this particular threshold, right. So, how a comparator works? If you recall the working of a comparator, and if I observe this, okay, let us take this is plus and minus, this is V1 and this is V2 and this is V0. If you recall, so the V0 will be equal to plus VCC if V1 is greater than V2, right, and V0 will be equal to minus VCC if V1 is less than V2. Now, in this case if I see, V1 is nothing but our threshold, right. So, positive terminal is V1 and in this case positive we have connected to V1, that means the threshold value is 666 millivolt, and V0 is what? And our V2 is nothing but the input signal or the positive PQRS wave, right, only this particular part. Now, when we are passing that, we will get a peak only when this particular input, right, input is greater than this value, right. So, when the input signal is greater than 666 millivolt. So, say this is 666 millivolt, then we will get a peak value pulse. Now, we will see whether we are getting it or not. So, what I will do is that we will implement the same circuit. So, if you remember, so this particular portion will implement now, right. So, here we will apply the input, actual input signal, right. This input signal we are applying, and here it detects a peak and it generates a threshold, that we will compare with the input signal, and whether we will get pulses only when the input is greater than that or not, we will observe that. Okay. So, I will go to multisim once again. Let me save this circuit. Right. I am opening a new file, or to this itself we can create extension of it by using another comparator. So, I will go with the schematic and I will take one more op amp, right. So, let me flip it, and the negative terminal, when you look into our circuit, if you see to the positive terminal we are connecting the threshold value, and to the negative terminal we are connecting the input signal. Now, so just to identify, what I will do is that I will take one more resistor, some rough 1K value, and other terminal I will be connecting it to the ground, or you can connect it to okay. We will take the same circuit itself, we will take LED. So, I will take an LED, connect it here, and one more ground, let me connect it here. So, color is red, okay, that is cool. Now, when I see, let me run it. So, since the frequency is very high, we can see it is continuously glowing. So, make it as frequency, 1 volt, I will say 1 volt, okay. Right. Then this one, let me decrease. So, we have to analyze. So, 100 hertz is also really higher to understand. So, let me make it as 50, even that is too much, 30. Okay, go to grapher, and here let me change, let me increase the time division just to understand. So, what is happening here, that we have to understand. Now, so we have not connected voltage source here. So, let me remove everything, right. So, I will take one more voltage source, connect at this point, okay. I will take one more voltage source, connect at this point. Now, let me go to the split voltage, right. So, zoom it. So, to understand this, how do we understand? If I want to understand this, what I have to do is that I have to create a cursor. The input voltage is 1 volt. So, the cursor is, I will take y axis cursor and I will keep somewhere around, if we observe the cursor value, it should be somewhere around 666 millivolt. Okay, somewhere around roughly 679, and let me zoom little bit, so that easy to understand for us. Make it as auto or single, yes. Now, what to understand? One thing is clear, that the C1 represents our threshold and the green color represents our input signal. What about the blue color? Blue is nothing but our output. Now, what is happening? Whenever the input signal is greater than that, whenever the input signal is greater than the threshold value, what is happening? It is going to minus VCC, right? And whenever the input signal is lower than that, it is going to plus VCC. The reason why? Because we have used positive input. Yeah, here if you observe, the negative terminal is connected to here, whereas the positive terminal is connected to threshold. Now, when we recall our comparator working, one thing we are sure that the output will be higher only when the input signal is greater than this particular value, right? That is what we have seen in the calculation. Now, to quickly understand that, why don't we take some values? So, take a sine wave. I am taking a sine wave. So, let us say the value is 1 volt. So, I am applying a sine wave of 1 volt and the threshold value is 660 millivolt. Now, this is positive, right? So, in order to become plus VCC, V naught to be plus VCC, when it will become only if the input is lower than the threshold in this case, right? Suppose if the input is 0.5 volts, V1, so we are taking V1 as positive, V1 will be higher and this value will be lower. As a result, V out will be plus VCC. So, that is the reason, but we require in a volta way. So, that means if I make this as a positive and this as a negative, right, then what happens? Since it is 666 and this is the sinusoidal wave till okay, when the input, so this is a threshold. In order to become V naught as higher, the input voltage should be greater than the negative value, only then it will become higher. Now, let me go to schematic, just to stop the circuit. I will swap the terminals. Okay. This particular terminal should be connected to here and this is here, and this particular terminal should be connected here, right, that is input, and here I am going to measure the threshold value and this is okay. Now, let me run it. So, grapher. Now, see what is happening? Yes, when we observe C1 is at what point? C1 is at 679 millivolts. So, we require 666. Now, when we see the output is becoming higher only when the input is greater than this particular threshold. Now, what is other color behind that value, behind the C1? That is our blue color, that is for the threshold. So, here if you remember the schematic, we have used one at this point, other one is at this point, light blue, sky blue and dark blue. So, here if you see, this is the output and the sky blue color is somewhere here. So, that is our threshold, right. Now, whenever the input is greater than the value, we can also see the LEDs keep on blinking it, right. If I change the input voltage, even thresholds, everything will change. So, let me make it as 5 and change this to auto, right. We can see threshold is also changed and even right, this is the input and this is the threshold and this is the output that we are getting it. So, that means that the thresholding part, everything is working fine for our application. Now, we will see experimentally, right, we will see experimentally of complete circuit. Now, if you see the next part of this particular portion, so we are using a diode, right, and we are also using a resistor, right. This the diode and the first quadrant portion of the op amp is using that the half wave rectifier portion. So, in order to verify that circuit, what we do is that now the input we will connect it to the input signal, we will connect it to the input of operational amplifier, that is at the pin number 3. So, what I will do is that I will take the input sinusoidal signal to 3 volts to the third pin. So, the third pin is somewhere here, okay, and this is the output. Okay. And which is the output in this case? The output is after the diode. So, that is somewhere around, when you recall the circuit, the output is the cathode terminal of the diode, right. So, the cathode terminal of the diode is connecting it to the second pin. Second pin is or nothing but a inverting terminal of our op amp. Now, if we see that, in this case I will take one more wire, or I will take the second CRO probe and I will connect the second CRO probe to the third pin, the second pin. So, third pin is input. So, I am connecting it to the third pin of the input signal, and the second pin is the output. I am connecting it there, right. Now, so let me auto set it. So, we can keep it at any frequency, there is no problem. When we look into the oscilloscope, so what I will do is that I will change a little bit down to the same value. From the signals it is clear that, right, only one peak we can see in the output, only one peak we can see in the output, and other peak we cannot see that. That is because of half-wave rectifying. So, we are removing complete negative peak signals of our input signal by using a simple diode. Why? The reason is that we have to find out only the positive peak, we do not need negative signal processing in this case. So, that is the reason we are going with the removal of a negative signal. Now, if I observe, so there is no negative signal. Whenever there is a negative signal in the input, the output is 0, and positive signal it is passing through, output is 0 when there is a negative again. So, that means it is completely removing our negative part, negative peak of our signals, negative signals at all. So, even if I change the frequencies, no matter what frequency that you are at, so it can only pass positive frequencies, not the negative frequencies, sorry, positive input signal, not the negative input signal, right. So, that means that particular portion, whatever we have seen in the simulation and what we are seeing in our experimental, the peak, the half-wave rectification is completely done. Now, what is the next part that we have to see? After passing through the half-wave rectifier, we have to find out the peak. So, in order to do the finding out the peak, if you remember, we are using a capacitor. Now, in this case, if you see here, the other part of the operational amplifiers in the board, right, when we look into the board, right. So, this part we are using a capacitor and we are using the resistors of 1 mega and 2 mega, right. This combination, this particular combination will give us the peak, the peak detection as well as the thresholding. So, now what I will do is that, so since we have already connected to this terminal and the output of this is connected to the next portion of our circuit, it is nothing but the peak detection. So, it is already connected using the white color wire here, the output of this, and now what I will do is that the output of CRO we will take the output of CRO. So, we will connect this particular point to the cathode or the sixth terminal in this case. So, this is my output, right. When we see that, when we look into the oscilloscope, the input is yellow in color, input is yellow, and the output is the sky blue in color, right. We can clearly see that. Now, the output is very the output is completely at the peak value of our input signal. Now, what if I change the frequency? It remains the same. What if I change my amplitude, right. So, now let me increase the amplitude value. So, right now it is the peak value of 1 volt, if you see that the peak value of 1 volt, because we are applying amplitude of 2 volts peak to peak, 1 volt on the positive peak and 1 volt in the negative peak. So, the 2 volts peak to peak value, I am increasing the voltage. So, I will go to the amplitude, I will change it to 3 volts, that means 1.5. Now, see the capacitor, because of 1 microfarad capacitor, it is quickly charged and it has gone to that particular peak value. Now, if I slowly increase, even then we can see. So, it is always, but whereas when I am decreasing it, we can observe that the capacitor is slowly discharging, and but whereas when I am increasing it, we can see quick rapid change of going to the peak value. So, that means we can understand that with this circuit we can easily find out the peak value of the input signal, right. So, the peak detection part is done. Then the next part is, once the peak detection is done, we have to create a threshold. Now, if you recall our circuit, we are creating the threshold by using two resistance, that is of 1 mega and 2 mega resistor. Why we are using such a high resistance value? Again, the reason is that not to have any loading effect into the system. So, what I will do is that now this particular output terminal, the blue connection, I will connect it to the junction, the resistor junction. So, when we see that we have connected an output at this point, right, which is the combination of 1 mega and 2 mega resistor. So, what we are using it at the node of 1 mega and 2 mega, we have connected the output. So, here if you can see, we have applied input frequency of 100, right, amplitude peak to peak value of 2, that means peak value of 1 volt. Now, when we see the output, this is the yellow represents our input, and we can see that the output is in blue color, right. The peak value is of 1 volt, 1 box, and the blue color, if I see, it is 2 points. So, somewhere around 486 millivolts we are getting it. The reason why there is a difference in the actual calculated value and the experimental value, it may be because of some loading due to the previous stages, or maybe because of the tolerances that we have, that since we have used 1 mega 2 mega resistances, the tolerances 5% tolerances is enough to change the complete resistance value of that to different other values. So, because of that tolerances and because of some previous loading stages, it is changing some other, it is going to show some other threshold value. But as long as even though my input voltage is changing, if that is maintained constantly, my problem would be okay, or I can replace some other resistance value and we can see whether it is whether it is having the required threshold or not. But when we apply DC input voltage and we do the experimental, and we can see the complete theoretically we can see that 666 millivolts it can be achieved, and even in the simulation we have seen. Now, what I will do is that I will change the amplitude to somewhere around 4 volts. So, if it is a 4 volts, it should be, so previously it was 400, now it should be 800, right. Now, if I see, previously it was in 2 levels, now it has moved to the 4 levels. So, closely towards 1 volt, so somewhere around 800 millivolts. So, that means when the input is keep on increasing, the threshold value is also increasing. Let me change to some other value, 6, so it is 1.2, right. So, either maybe because of the previous loading or because of the tolerances due to the resistance value, the threshold value expected and the actual are little different, but by putting some potentiometer, we can even set it to the required threshold value in this case. Now, what is other stage that we have seen? Other stage is we have to pass through the comparator. So, we have to connect the negative input of an op amp to this particular point and the positive input to the input signal. So, that when we do in that connection, we can see the output of an op amp to plus VCC state, right, whenever the input is greater than the threshold. So, what we do is that when we look into the board, what we do is that we will connect the positive terminal to input terminal. So, positive in this case is 10th terminal. So, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So, this terminal I am connecting it to the input, right, whereas other terminal I should connect it to the output. Okay. I will remove this wire. So, this is our threshold, right. To this threshold point, I am taking one more wire, I am connecting it to this point. Now, I have to measure the output. So, this is my output. Let me auto set it. When I look into oscilloscope, right, so let me keep both the things to the same point, so easy for us to understand, and this point to changing the offset value, right, and the input also I will change to the same 2 volts peak to peak, so easy to understand, and let me change the input range to 5 volts, right. So, both are at the same point. So, since it is difficult to understand, what I will do is that I will change the input amplitude itself to somewhere around 6 volts peak to peak. So, that means 3 volts. So, here it is clear. Now, if you remember the threshold, the theoretical threshold for 3 volts would be 666 millivolt into 3, but practically we are getting 1.2 volts, right. So, practically we are getting somewhere into 1.2. Now, when we observe that, one thing is clear, that when I say, if I take a cursor, I will take a cursor of amplitude type, I will just keep somewhere somewhere at 1.2, that is what theoretically when we measure we are getting the practically when we measure we are getting at that point. Now, I place the cursor at that point, it is clear that so, when we look into that, it is clear that when the input, so the cursor LO1, when you look into the CRO, this particular cursor, consider it as a threshold for ours, whatever we have calculated practically. Now, when the input is greater than that particular threshold, we can see there is a high value. High in this case is 15 volts, because the VCC and minus VCC that we are applying is plus 15 and minus 15. It is close to plus 15, it is slightly below plus 15 because of the saturation. The output saturation will be lesser than the VCC that you are applying to that. And when the input is lower than that particular value, it is again going back to the minus VCC states. But when we look into the board, we can see the LED is continuously glowing. We cannot see any flickering of an LED like on off on off. The reason is the frequency. When we see the frequency that we applied is 100 hertz. 100 hertz, it is very hard to understand with our eyes. So, what I will do is that I will change the frequency to somewhere around human understandable values. So, somewhere around 30 or 20 hertz. So, where we can easily visualize it. When I see that, right, since the frequency, when you look into the oscilloscope, so we can see we have kept somewhere around 30, and even in the oscilloscope, so we can see the input is 30 hertz frequency, oscilloscope we can see the high value, and when you look into the breadboard, right. So, whenever it is higher, the LED is starting glowing. So, when we look into the breadboard, we can see because of the smaller frequency, right, we can see the on and off of our LED too. Now, if we connect to a digital counter, the output of this to a digital counter, one thing is clear that we can easily count how many number of pulses we are getting it, right. And if we create some clock cycle for different for this particular time period, how many number of frequencies that we are getting, right, that gives us how many BPM, beats per minute. So, we have seen individual subsystem point of view, how whether it is working as per our requirement or not. Now what we have to do, we have to take a subject or we have to connect particular person, we will connect the ECG electrodes. So these are the ECG electrodes connected to the person. So one at right hand, other one at right left hand, and other one the ground is at right leg, that we have discussed in the starting of our experiment, right. And here we will be connecting to this metal pins, we will connect the electrodes and we will see whether we are getting ECG signal or not in a oscilloscope. Then what we do is that we will pass through amplifier for amplification of an ECG signal. Until unless we do the amplification, it is very difficult, very hard to detect using our normal DSOs, because the amplitude of the actual ECG signal is very poor, right. So in order to improve our signal ratio, we are passing through the instrumentation amplifier, then we will pass through filtering, so that we can easily visualize whether the signal has been filtered or not.